This is the third video on the topic of matrices and eigenvectors. The link to the other two videos is in the description. I talked about the concept of eigenvectors and eigenvalues in the first two videos, and in this video I am going to illustrate a practical application of matrices using a real-life problem. I'm going to model a very simple viral infection scenario to explain how matrices are used to calculate population dynamics, and how individuals transition between being infected and recovered. Imagine that you are part of a community of 200 people. One day, there is a spread of virus in that community. Now let us assume that the rate of infection per day is 15%. Which means that every day 15% of the people get infected with virus. We also know that people recover from the virus. So let's say that the rate of recovery per day is 10%, which means that every day 10% of the infected recover. Now I want to see the spread of this infection after several days in the community, and how many people will be healthy and how many will be infected after a few days. So I want to find that out. So how can I proceed to solve this real-world problem? So I start by writing down what we know about the system. I know that the system is a dynamic system because the population will change from healthy to infected, and then some infected will recover and become healthy again. I know that the population of healthy people is 200. I also know that the population of infected people on day 0 is 0. Now I also know that the rate of infection per day is 15%. And the rate of recovery is 10%. So initially, what is there on day 0? 200 healthy people and 0 infected people. So I can say that the initial conditions are population of healthy people, 200, population of infected people, 0. And then what about the rate of infection and rate of recovery? I can say that these represent rate of population change, because population will rotate between healthy and infected based on the infection and recovery rate. Rate of infection per day is 15%, rate of recovery per day is 10%. So I can think about the problem in terms of initial values and rate of population change. So now you see how I have broken down a real-life scenario into a logical mathematical structure, and this will help me solve the problem. So now I can calculate what happens on day 1. The viral infection started on day 0, so healthy population on day 1 will be 85% multiplied by healthy population on day 0. Why 85%? Because 15% is the rate of infection per day. So every day, 85% of the population remains uninfected. So 100% minus 15% is 85%. So healthy population will be 85% multiplied by 200 plus rate of infection, which is 10%. Multiplied by infected population on day 0, which is 0, because there are no infected people on day 0. So this gives me 170 healthy people on day 1. So now let me calculate infected population on day 1. So the infected population is rate of infection per day multiplied by healthy people. So this is 15% multiplied by 200 plus the infected population who do not recover, which will be 1 minus 0.1 multiplied by infected population on day 0. But at the start of day 1, the infected population is 0. So this gives us 30 infected people on day 1. Now we can also quickly subtract 170 from total population and get 30, which is the infected people. But it is better to use the equation because for larger and complex communities, simple subtraction of healthy from the total population will not work. So I have developed two equations, one for calculating the healthy population and one for calculating the infected population. And how cool is that? I have morphed the real-life scenario into two mathematical equations. I started with the problem, I broke it down into initial conditions and what is causing the change. Then I developed the equation. This is what practical application of mathematics look like. And this is a very simple example of applying mathematics in real life to solve problems. Now I can write the rate of population change as this: 0.85, 0.10, 0.15, and 0.90. And I can write the population on day 0 as 200 and 0. And the calculated population on day 1 as 170 and 30. So does this not look like matrices multiplication to you? It does, doesn't it? So wow, I just created matrices for this problem. Isn't that amazing again? I developed two equations to calculate the population, and then I transformed the equations into matrices. This is the beauty of mathematics. It is interconnected and can take many forms. Mathematics is like a shapeshifter. And now, when you think about it, this is why matrix multiplication works in this way. Because the multiplication is the same as how you would multiply in an equation. So now I have developed a set of equations and matrices which serve as a model to represent our dynamic community and its behavior. Now, instead of numeric values, I will replace the numbers with variables in the equation so I can develop more general equation for population model. I will call the healthy population pH. I will call the infected population pi. I will call rate of infection per day Ri. I will call rate of recovery or rate of cure per day Rh. And then the two equations can be written as this. Now PHF and PIF are healthy population and infected population. And these population numbers will change every day because people will keep getting infected and some will recover. To further polish the equations, I can write the equations as this, where RHR is 1 minus RH and RIR is 1 minus RI. So healthy population rate is RHR and infected population rate is RIR. And the matrices will now look like this with the variables. Now I can use any population number, be it 300, 500 or even 1000, and any infection and recovery rate to calculate population on different days using these general equations. So this is why I developed a general set of equations and matrices. So when I look at these two matrices, which one of them is causing the population to change? It is this matrix, right? The matrix which has rates of population change. And which matrix represents the state of the community? Is it this matrix, right? So let's call this matrix as transition matrix, and let's call this matrix as state of the community. Now why is this called a transition matrix? Because it makes the population distribution to transition from day 0 to day 1 and so on. Meaning it helps us calculate the changing population of healthy and infected people every day. So basically it helps us calculate how population transitions from one day to another. Now this transition matrix is also called Markov matrix. It is named after Andrei Markov, a Russian mathematician. And like I said, it can be used to predict future state of the system. In our case, the system is the population of healthy and infected people. In this resultant matrix, I will call it the future state of the economy. One thing I will add here is that matrices are very useful for problems where rate of things change in a system. In our case, it is the rate of change of population. So matrices are used in advanced mathematics to solve dynamic models involving rate of change. So now I can write these matrices as this, basically writing them in an equation form. So you see how equations and matrices are interconnected? That's so cool. So coming back to the population of 200, on day 1, I have 170 healthy and 30 infected. Let me calculate for day 2, and it will be this population on day 2. 147.5 healthy and 52.5 infected. And I will calculate the population for a few more days. I think I will reach a point in time where both the healthy and infected people will be in a state of equilibrium if these initial conditions don't change. In real life though, the rate of infection will decrease with a combination of increased medication, vaccines, people developing natural immunity. But for our understanding of how matrices work, we will assume that rate of infection remains same. So I've calculated the population till day 100, and I see that on day 10 there are 87 healthy people and 113 infected people. On day 20 it is 80 healthy and 120 infected. And I keep on calculating it further and further. What I found was that on day 50 it is still 80 healthy and 120 infected. And even on day 100 it is still 80 and 120 infected. So I can see that after day 20, the population of healthy and infected people does not change. This means that after 21 days, 22 days, 23 days and so on, the population distribution will remain unchanged. Let us say if 4 people get infected on day 21, then 4 people will recover and get healthy on day 21. If 5 people get infected on day 22, then 5 people will recover and get healthy on day 22. So the population of healthy will remain 80 and that of infected will remain 120, meaning there is a balance between the healthy and infected. So I can say that the population distribution stabilizes after day 20. So this matrix, which does not change after multiple days of calculation, it represents the steady state of the system, and I can also call it eigenvector. And this eigenvector represents steady state population distribution at the equilibrium point. And this is a very important concept in matrices and population dynamics. Eigenvector tells us the equilibrium point of a dynamic system. It describes the state of the system at equilibrium, and it does not change once the system reaches equilibrium. Like we have seen in this case, that after day 20, the number of healthy and infected people does not change. So it is very useful in understanding the problems where rate of change causes transformation. So eigenvector is the point where the system stops changing because the rates of change in the system have balanced out. It's very important to keep that in mind. And because it is called eigenvector, it means that it is a vector. And let me plot it and I will show you why it is called a vector. On x-axis I have healthy people, on y-axis I have infected people. Because it is a vector, its rows represent coordinates. So we can plot this vector and it will look like this. Now let us plot the vectors for day 1, day 2 and day 10. So these are the vectors for these days. You can observe one thing, that the vectors for day 1, day 2 and day 10 are shifting towards y-axis or are shifting to the left side of the graph. This means that the vectors are rotating counterclockwise with every passing day. And if I plot vectors for all the days between 1 and 2, they will be all moving closer to the eigenvector. This is because the population distribution is trying to move towards an equilibrium state. And these vectors show the daily changing population distribution. Every day, these vectors move closer and closer to the eigenvector. So basically, I have represented the population distribution with a vector. Now, how cool is that? Visualizing how population changes with the help of vectors. Another interconnectivity of mathematics and its shape-shifting. And once the equilibrium state is reached, the vector will stop rotating. And the vector at the equilibrium state will be eigenvector. Because there is no more change in the population distribution after that, as long as the system conditions remain the same. System conditions in this case will be rate of infection and rate of recovery, and no outside influence such as no people leaving the community or no people entering the community. So just to reinforce the point about the eigenvectors, they represent steady state population distribution at equilibrium. And in this case, eigenvector means that the population distribution remains unchanged after day 20. So I've done this calculation for a community of 200 people. So how can this eigenvector be used for communities with larger population? If those larger populations have the same rate of infection and recovery, then I can use this eigenvector to find the steady state point of the population distribution of larger communities. Let us say there is another community with a population of 400 people and it has the same infection and recovery rates. So dividing 400 by 200, it gives me 2. Multiply the eigenvector with 2 and I get a new eigenvector with 160 healthy and 240 infected people for a population of 400. So this basically is an eigenvector. So basically the eigenvector doubled in magnitude because the population doubled from 200 to 400. So this 2 is the scaling factor because it scales the eigenvector in magnitude. And this scaling factor is also called eigenvalue. It is called eigenvalue because it increases or decreases the magnitude of eigenvector. An eigenvalue is a scalar entity, unlike eigenvector, which is a vector with both magnitude and direction. And the reason it is a scalar entity is because it only changes the magnitude of eigenvector. So let us plot this new eigenvector for 400 people. Let me adjust the scale of the graph. Let me call this eigenvector for 200 people. Let's write down the angle it makes with the x-axis. So the angle is 56.3 degrees. Now the eigenvector for 400 humans will look something like this, with coordinates of 160 and 240. So you see, it only scaled along the same line or in the same direction. It did not change its direction with respect to x-axis. It has the same 56.3 degree angle. So eigenvector is one which only scales along the same line of action and does not change its direction. This is why eigenvector is useful in studying population dynamics for viral infections or for predator-prey model and other similar problems, because it helps scientists understand the equilibrium point of population distribution in various ecological systems or in epidemiology. Now to write it in matrix form, this can also be written as 2 multiplied by the eigenvector for the community with 200 people. The answer is still the same. This is a simple example to illustrate the concept of matrices and how they are used in real-life problems, and also to illustrate the concept of eigenvector and eigenvalue with practical example. Now for more complex systems, we can use more detailed mathematical models. There will be more equations, there will be more complexity, but the key is to understand the problem, identify the initial condition, identify what is causing the change in the existing system, developing equations, and then solving the equations to get an answer. And then when you get an answer, just observe the answer to get some insights. Like the insights we gained from our answer in this case were that the population distribution stabilized on day 20. The eigenvector was 80, 120, with 80 being healthy and 120 being infected. And we also observed that the eigenvalue only causes the magnitude of the eigenvector to change. And an eigenvector is a vector whose line of action does not change, only its magnitude changes. Hope this is useful. Cheers!